Now it's going. Whoops. Okay. Now we should be good. Okay, sorry. So, access page 1, what happens? So, yeah. Yeah, so if we look back, so we check the reference hand. Currently it's 0, so we place the page there and advance the hand. So currently we're pointing at something, its reference bit is 0. In fact, it doesn't represent anything. So we place page 1, so that's the number at the top. Its reference bit would be 1 because we just used it. Then we advance the iterator to the next spot. So everything goes clockwise. Hey, it's a clock algorithm. All right, what happens if we access page 2? Hopefully exactly the same thing, right? So not pointing at anything valid, its reference bit is 0. So I'll place it there, place page 2 there, reference bit is 1, advance the hand. Can we skip 2 steps? So should not be terribly surprising. So access page 3, I insert it right there, reference bit is 1, advance the hand. Same thing for page 4. Insert it right where it's pointing because its reference bit is 0, advance the hand, and its reference bit is now 1. Now what happens if I access page 5? Yeah. Eventually, wow, we're already fast at this. So, excruciating detail. What do I have to do if I follow it one step at a time? Yeah.
Each reference bit to 0 until you get to this index here.
Yeah, so the slower version of exactly what you said. So currently pointing at something, the reference bit is 1. Can't get rid of it. I essentially give it a second chance. Change it from a 1 to a 0. And well, because it's set up like this, it's going to be boring. It's going to go around. So 1 goes to 0, advance it. 1 goes to 0, advance it. 1 goes to 0, advance it. And finally, we wrapped all the way back around to the beginning. Now we can replace page 1, right? Its reference bit is 0, so it's out of here. So we replace page 1 with replace page 1 with page 5, set its reference bit to 1, and move the hand. So now our clock looks like this after we insert 5. Now what happens if I access page 2? Yeah. Yes, just set the reference bit to 1. So before, when we had FIFO or whatever, we weren't keeping track of things. We just set it was a cache hit, carried on. In this case, we're setting a reference bit. So in this case, since we just used page 2, kind of makes sense. We accessed it, so we'd set its reference bit to 1. The idea being, well, we just used it, so we wouldn't want to get rid of it immediately because we just used it. So we just take page 2, set its reference bit from 0 to 1. Good? All right, access page 3, what happens? Same thing. Set its reference bit from 0 to 1. All right, page 1, what happens? Yeah.
Just a clarifying question. If your hand is pointing at some other index and that's not the page you want to look at, do you not have to traverse through and set the bit to 0 and then when you get to, in this case, you wouldn't have to set choose reference bit to 0 and then move to 3 and then so.
Yeah, so the idea behind this is we want accesses to be as fast as possible. So you can think about it that way, that, well, all I'm doing is updating a bit. I'm not touching the iterator. I'm not traversing anything. I'm just setting a bit, and that's all I'm doing. So even it doesn't matter what the iterator is currently pointing to. That's only for replacement. For keeping track of accesses, doesn't matter. I'll just flip the bit. Yep. No, it's just going to follow exactly whatever the current hand's pointing for. It'll just follow the algorithm, whatever it is.
So like if you want access 3, but 4 was before it and had a 0 bit, is it going to replace it?
Yeah, it should replace it. The first time it hits 0, it replaces that one, right?
Even if you have so we have 2 3s.
Oh, you wouldn't have 2 3s, no. Only one page in memory at a time. So you wouldn't have 2 entries where one's referenced and one's not. It's just, is 3 in memory, yes or no? Yeah.
So the iterator only moves when you add
Yeah, iterator only moves when we're actually doing the replacement. Because the idea behind that is, on accesses, we want to be fast, right? Can't do anything but faster than just setting a bit without doing nothing. So, only change the iterator once we're actually doing the replacement algorithm, once it is not in memory. So, in this case, what's good? So now I access page 1, and well, previously I set 3 from a 0 to 1. So now what happens when I access page 1? So it's not currently in memory. I have to kick something out. Yeah, I would eventually kick 4, but first step, well, if I follow the algorithm, then I'm currently pointing at a page 2. Its reference bit is 1, so I can't kick that out. So I change its reference bit from a 1 to a 0, so it essentially, you give it a last chance. So I move the iterator to page 3. Well, its reference bit is 1. I change it from 1 to 0, move the hand, and now I point at page 4. Its reference bit is 0, so it is now gone. So I replace page 4 with page 1, set its reference bit to 1, and advance the hand. So now after I have inserted page 1, it looks like this. So any questions about that? All right, so now I access page 2, what happens? Yeah, sets the reference bit to 1. Don't need to touch the iterator. We want to be as fast as possible. So 2, its reference bit goes from 0 to 1. And for the last access, page 3, it goes from a 0 to a 1. And it looks like that at the end of the day. Now, if I draw that out in terms of page faults and what we had before, this is what it would look like. So it would begin looking exactly like FIFO, all of our page replacements. But if I just write them out, whenever we access 2, well, it didn't look like we did anything. We actually updated a reference bit. But if you write it out like this, just all the pages just stay in memory like we had before. Same for 3, although we updated a reference bit. And then when we access page 1, we replaced page 4, and then we went ahead and accessed page 2 and then page 3. How many page faults was that? 6. If I want to compare that to the best we could possibly do, what would I compare it to? For what? 6? All right, so the best thing we could do, what algorithm is that called? The optimal algorithm, right? So same page accesses, but optimal. So we can do am I okay to skip the same 4 steps of optimal, just bring it into memory? All right, so we are going to have some extra time at the end of the lecture. So these are a page, we just load everything into memory, and this is the state after the first 4 accesses. Now we have to bring in page 5. So what do I kick out to bring in page 5 if I'm doing the optimal thing? 4, right? Look in the future. Well, I can't kick out 2, I can't kick out 3, I can't kick out 1. That leaves me with 4. So I would replace 4 with 5. Oh, and then guess what? After that point, everything is a hit, How many page faults is that? 5, yeah. So 5. So got kind of close to optimal, but so clock got 6, optimal got 5, so hey, we did pretty decent. All right, if we really, really want to evaluate this, this is the sequence we used in the last lecture when we did like FIFO, least recently used all of them. So what, do we want to redo this with the clock? Sure, may as well. Otherwise, I mean, I guess you can go home right now if you don't want to do that, because that's pretty much all the lecture. So if I do that, before when we had all those accesses, we could fit 4 things into memory. So if we're doing the clock, we can draw ourselves some boxes, 1 for each frame we can hold. And let's just draw some nice arrows between them just to show that it's circular. So I can just leave it empty if I want. So what happens if, oh, and let's point at something. Actually, I'll make it blue. So the iterator I will do in blue. So if I access page 1, what happens? Yeah, we insert it in, reference bit is 1, advance the hand, right? Doot. So 1 goes in, its reference bit is 1, so I'll write the reference bit in blue, and then we advance the hand. So it would look like this, right? Can I skip a few steps? All right, we can skip a few steps. This lecture is going to be real quick. All right, so eventually, whoops, we will insert page 2, then 3, then 4, and the hand will wrap all the way around back to the beginning. We'll have reference bits like this. 2, 3, 4. All right, good. Any questions about how we got to that point? All right, this is boring. That's good, because guess what? Should be free marks on the final on the horrible day we got chosen for it. So what happens now if I access page 1? Nothing, right? Yeah, its reference bit is already 1. However you want to think about it, up to you. So it changes 1 to a 1, or this does nothing. Doesn't matter. At the end of the day, means the same thing. All right, accesses page 2, what happens? Whole lot of nothing. Whole lot of nothing again. All right, now things get interesting. Page 5 happens, or at least as interesting as it's going to get. So what happens now? Yeah, if I want to do a shortcut, if everything is currently a 1, to do a shortcut, I'll just change all the 1s to 0 and just go on from there. So change all the 1s, he said, to a 0. Then go on from there. So now I'm trying to insert page 5. So currently the hand's pointing at page 1. So I should probably kick page 1 out. Kick page 1 out for page 5. So I kick page 1 out. 2, 3, 4. All right, am I done? Yeah, I should advance the hand after I put it in, because otherwise I'd try and kick out something I immediately just put in. So that was our big trick of the day. All right, so now what happens? I access page 2. Yeah, reference bit just goes from 0 to 1. Nothing else happens. All right, access page 3. Hopefully same thing. Hopefully it's like, get me out of here level. All right, so if you can do this fast, you can hopefully do this in like 5 minutes on the final. You will be given a lot more than 5 minutes. All right, so that's what it looks like. All right, access page 5, what happens? Nothing, or it changes 1 to a 1, whatever you want to think of it as. All right, access page 2, what happens? Nothing. Nothing happening is actually good. It means we're not swapping things in and out of memory.
Sorry.
Yep.
I have a question. So when we have that 5 coming in, and our pointer is pointing to 2, so it's going to rotate.
No. So when we access 5 for accesses, all we do is update the reference bit, nothing else.
But you're pointing to 2.
Doesn't matter what it's pointing to.
Oh, so you just see that 5.
Yeah, so the reference bit, there'll be some hardware support probably with it too. So it knows exactly where it is and it can update it really quick. Doesn't have to use the iterator. The iterator is only for replacement. All right, yeah, now we access page 1. What do we do? So do I throw out page 2? No, all right, if I follow it, Well, it's currently pointing at the iterator. This is where I use an iterator because I have to do the replacement. Currently pointing at an element, the reference bit is 1. So I give it another shot at life. I change the 1 to a 0, advance it. Then I do the same thing again. It's currently pointing at a 1, so I change it to a 0, and then advance it. Oh, now it's pointing at an element where the reference bit is 0, so it is now gone. So see you later 4. We just replaced you with, what, 1. Replace you with 1, reference bit is 1, and then we advance the hand. So now, what did we replace 4? 5, 2. All right, turns out that was a poor decision to make, so now we're accessing page 4. Currently not in memory, so if I follow the steps, I shouldn't get rid of page 5. I should change the 1 to a 0, then advance the hand. Oh, now I'm pointing at page 2 while its reference bit is 0, so now it is gone. I put in page 4, reference bit is 1, advance the hand, and I replaced, what I replaced, page 2. All right, how many page faults happened? 7. Do we remember how many we had last lecture for, like, I don't know, FIFO? FIFO was pretty bad. I think it was like 10. LRU last time was 8 or 6, I forget. Optimal was 6. So, hey, it did pretty good. And guess what? We can actually implement it. So, any questions about that? Yeah.
When you go like the memory in a circle, is it really just like the memory is still just one block? It will just go down and that.
Yeah. Yeah. It just as soon as you hit the end, you go back to the beginning.
Does that mean like it rarely actually loops back?
Sorry?
Does that mean it's like rarely loops back to the beginning? It'll just keep going for all the blocks until
Yeah, it might loop back to the beginning, and depends if everything's full. So initially, every single time if it's empty, then we load it in, reference bit is 1, then we have to circle around the whole thing. So sometimes we might have to do that, but that's the worst case. Generally, after the first time, it kind of settles down a little bit, and we don't really have to do that.
But if you have like 8 rebytes of memory, then it's going to have to go through that.
Yeah, it might be slow, but it just goes until the first time it hits 0, and then it goes, and if all the bits are like right next to each other, then it's actually not that bad. So there's things you can do to implement to go faster. But just a bunch of bits will be quite fast, and you'll see you'll be using a bunch of bits in Lab 6 too. Yay, Lab 6. All right, any other questions for this? Yep.
Is there like a high level kind of like explanation as to why it's better than other algorithms that we use? So like
So high level explanation is 1.
is it better than other algorithms we use based on one of this example?
So far it's about the only thing we can actually implement. So right now we can only implement FIFO, and we can implement this. We can't really implement LRU because it's just too slow. So I think you could argue that this is better than FIFO by a long margin. But for this, point is, accesses, I do something really, really quick, and it kind of approximates least recently used because of just the reference bits. They don't keep track of like when I reference something, so it's not exactly least recently used, but because I go around in the same order and I essentially give things a shot, and whenever they're accessed, I set it back to 1, it kind of approximates that. It's kind of the idea. So it looks like least recently used-ish with using only 1 bit of information to keep track of when something was used. Yep.
What would we get a different order if we used least recent use? What would the difference be?
So Yeah, we get slightly different orders depending on this if we tried to do least recently used. So I forget what we had last time, but I think it was 6-page faults maybe. So least recently used I think was better. So last lecture we did the exact same sequence I think. But in general, least recently used is probably going to be slightly better, but we can implement it. Alrighty, so any other things for the last point? All right, so for the last point, for performance, I think I touched on last lecture, I'll touch on it again. So for performance, the last 2 lectures might not also be important to you because, well, it goes really slow. If you start swapping to disk, instead of using memory, you're using disk, and you can't really control it. Suddenly, if you kind of run out of memory, your program just starts running slow. You might not want that, especially if you're Google. You would rather just run out of memory. So if I don't have swap and I run out of memory, what happens? In your program, so if in your program you ran out of memory and you tried to malloc something, what would happen? So exit seg faults. So all right, so none of us actually check for errors, do we? Malloc returns null. And you should be able to detect that and like quit gracefully, but I guess no one actually does that. So remember I've told you in this course to check for errors. It will probably take you about, depending on what job you go to, probably like 2 to 4 years to actually start listening to me. So just remember I told you so whenever it finally clicks. So yeah, if I don't check for errors, then I would get a null and then I would probably seg fault and it would probably be hard to debug. In fact, also, well, the kernel, depending on the out of memory thing, the kernel can also check. So the kernel will know if it has run out of memory because, well, it's a kernel, it's managing memory. So what it will do is run something called the OOM killer. Any ideas? Oh, I put it on the slide. So OOM stands for out of memory. So the out of memory killer is not very complicated. You can just look through all the process control blocks, see what's using the most memory, and essentially sig kill it, and then it's gone, and just free the memory. So that's an easy way to resolve an out of memory issue. If you're the operating system in your process, it's a bit harder because you can't just do whatever you want. But the kernel can just kill a process, freeze the memory. Process it kills, probably Chrome, let's be honest. So now you got lots of memory. So other things it could do, and yeah, another reason to disable swap is, yeah, if you're Google and your program just crashes or seg faults or you actually detect it, instead of running slower, you just go out, buy more memory, whatever. I think I said that last lecture. So there's also another thing we can do to kind of speed up things that is a different approach. So the page size of 4 kilobytes, that was decided at some point in the 70s. So now, especially for newer processors, I think x86 will do this. It will allow you to have multiple page sizes. So remember when we had like a 3-level page table, we had like 9 bits for L2, 9 bits for L1, 9 bits for L0, and then the 12 bits offsets. So what some memory systems will allow you to do is essentially get rid of the lowest level and then make your page size bigger. So instead of having a 2 to the 12 page size, it will let you have a 12 plus 9, so 2 to the 21 or 2 megabyte page size. So in your L1 page table, instead of pointing to an L0 entry, it would point to a 2 megabyte page instead. And that way your pages are a lot bigger, and essentially you're trading fragmentation for more TLB coverage. So imagine your TLB can only hold 4 entries, or 10 entries, let's say, for a nice number. If my page sizes are only 4 kilobytes, then essentially that TLB can only have essentially 40 kilobytes of memory space cached. If I have 2 megabyte pages and I can still only fit 10 entries, guess what? Now I have 20 megabytes that I cover in those 10 entries. So it's more likely that my TLB entries will still be in the cache. TLB is a cache, so it's more likely my entries will still be in the TLB. Things will go nice and fast. So any questions about that? Yep.
Question on the out of memory killer. Is it like only when we reach the point where we're out of memory, it'll like initiate the set kill on memory hog, and then
Yeah.
it does that when we reach no.
Yeah. Oh, so the out of memory killer only runs like the kernel. That's part of the kernel's job. It will only run when it has run out of physical memory and swap space. So there's literally, it can't get a new page anywhere. So if it can't get a new page anywhere, it's got to make space somewhere. Probably kills Chrome or whatever you want to pick off. One algorithm for the out of memory killer, sometimes it's not even that smart, just picks a random process and kills it. And if it picked wrong, just kills something else until there's enough memory. So you don't have to be, it's like, what's the saying? Shoot them, ask questions later, that kind of thing. So kernel can just shoot the processes and see if it fills it up later. All right, the other option is in some extreme cases, if you just go and remove 2 levels of page tables, gets your page size up to 1 gigabyte, but then, well, that's where we can really see that the fragmentation or internal fragmentation becomes a problem. So if your pages are a gigabyte in size and your program is only using, 10 kilobytes, well, guess what? Most of that page is actually wasted and you can't do anything about it. So probably you don't want to go up to this. So these are called gigapages, and the 2 megabytes, if you've seen in your operating system at all, they are called huge pages. I even think Windows on the activity monitor will tell you how many huge pages it's using. Huge pages just mean the 2 megabyte pages instead of 4 kilobyte. All right, any other questions for today? All right, we sped run that one. I don't know how some people take 2 lectures to go over clock algorithm. I have no idea. All right, so key data structures for clock algorithm. Circular list of pages in memory, uses a reference bit for each page. We put in light gray, do whatever you want. Has a hand, which is basically an iterator that points to the last element that's examined, and we only update it when we're actually doing the replacement. If we're doing the replacement, what we do is we check whatever the hand is currently pointing at. If its reference bit is 0, we replace it, add in that new page. That new page's reference bit is 1, since we just used it, advance the hand. Otherwise, if we're currently pointing at something with a reference bit of 0, well, we change that, or reference bit of 1, sorry. We change that 1 to a 0, advance the hand, and we just keep going through until we find a victim. And then the whole idea behind this is for page accesses, we do something really, really fast. We just set the reference bit to 1. Doesn't matter about the iterator or anything like that. So, anything else before we end? All right. Yep.
Where is the reference bit being stored?
So the reference bit can be stored in a giant bitmap, which might not make sense to you because we'll see that term next lecture, and we'll see it also in lab 6. But you can just essentially just allocate some memory and just have all the bits right next to each other. Or it could be part of the MMU system, so for each page it just keeps track of a bit. You could also use it in the page table entry itself. Most of them will, if we go back to the page table entry, one of the bits is actually a reference bit in the RISC-V one we saw. So your MMU will just update that for you. And so it'll be stored on the page table entry itself. All right, informal poll. So our midterm or final date is some ridiculous day where you get no time whatsoever. So the last lecture I was planning on doing review. Do we want the last 2 lectures to be review? Yeah, sure. Okay, done. What?
Yeah, what was the original plan?
So the original plan was I just make up something that I wouldn't put on the exam anyways and just talk about it. Or we just have 2 reviews. All right, two reviews it is. That gives you also like the week before off. Maybe not for you, but it gives you the Friday you don't have to worry about for the week. You essentially get a study week for this course, which is the best you could ever hope for considering you're the first day at the first time. So take advantage of that. And yeah, I guess we'll do 2 review lectures. So just remember, pulling for you, we're on this together.